Hi, in this video, we'll be talking about graphs, just the basics. So, what is a graph? Have a look at the following picture. It might represent a new road system for a new means of transportation, for example. It's very intuitive. Just by looking at the picture, we can say that you can go from Charleston to Detroit through Cincinnati or through Washington. You can also see that if you want to go from Denver to Dallas, you have to go through Kansas City and Cincinnati at least. But if you enjoy traveling, you can choose to go through Kansas City, Chicago, Detroit, Boston, New York, Washington, Charleston, and Cincinnati, for example. What you can see in the picture is an example of a graph. The red circles are called nodes or vertices, and the blue lines connecting the nodes are called edges. The nodes in our example are strings, the names of the cities, but they could be anything. Some nodes are connected by edges, like for example New York and Boston. Others are not connected, like for example Charleston and Dallas. In our case, we can move in both directions along the edges. So for example from Chicago to Kansas City and then back to Chicago. We call such edges undirected edges, and the whole graph an undirected graph. If we could move only in one direction, we would have a directed graph. Well, this video is just about the basics. Let's keep it simple and let's simplify our graph by reducing the number of nodes and changing the names of the cities to their lowercase initials. Here's the new image. So after a year, the new means of transportation turned out not to be very successful. It was reduced. In this graph, we have 6 nodes, one of which, K, is not connected with any other one with an edge. The numbers of edges from the other nodes are also differentiated. There's 1 edge from C, 2 edges from D, B, and N, and 3 edges from W. In order to represent the graph in code, we can simply use a dictionary. The keys will be the nodes, and the values will be lists of neighboring nodes. By neighboring nodes, I mean nodes directly connected by an edge with a node which is the key. Here is the dictionary. As you can see, the K node isn't connected with any other node, so the value corresponding to it in the graph dictionary is an empty list. We call such nodes isolated nodes. All the other nodes are connected by edges. An edge can be represented by a 2-tuple containing the 2 nodes on either side. So the edge between B and W could be represented in code like so. A tuple, the first node B, and the second node W. Okay. With our graph dictionary in place, we can generate the edges. That dictionary contains all the information that is necessary to do that. Here's the code. This function returns a list comprehension, and the list that will be created will contain tuples representing the edges. I'm using a list comprehension here to create the list of edges, but you could use a for loop instead. If you want to learn more about list comprehensions, I have a video about them, so feel free to watch it. Let's use the function and print all the edges. Print the following edges have been generated. Here we're using the function edges. And now let's run the program. The following edges have been generated. BD, it's from B to D, BN, from B to N, CW, from C to W, DB, from D to B, DW, from D to W, and so on. There's just 1 isolated node in our example, but there could be more. So let's write a function that returns a list of all isolated nodes. Isolated nodes, here we pass our graph as the argument, return, and another list comprehension, node for node in graph, if not graph of a node. I'm using another list comprehension here. Note that instead of writing if graph of node equals an empty list, I wrote if not graph of node. This is possible because an empty list is understood as false in Python. Okay, we don't need that. And now let's print out the isolated nodes, or in our case, the one isolated node. Print, the graph contains the following isolated nodes. For node in isolated nodes, print node. Now let me comment out this part of our code because we don't want to print the edges again. Fine. And now let's run the code again. The graph contains the following isolated nodes, k. And this is correct. K is the only isolated node here. We already have two functions, edges and isolated nodes, and we're going to have even more, so it seems reasonable to wrap the whole functionality in a class. Let's do that. So let me first remove this. Now let's create a class. Class graph. Now the init function. So we can initialize an object with an existing graph. If we don't, an empty graph is created, which is represented by an empty dictionary. This is the default value. And here's our edges function turned into a method. It returns the list of all the edges. Now that we have a method that returns all the edges, let's create a method that returns all the nodes. We must convert the case view, which is returned by the case method, to a list. If you want to learn more about dictionary views, I have a video about it, so feel free to watch it. And here's the isolated nodes method, which returns all the isolated nodes. We'll define two more methods, one for adding new nodes and the other for adding new edges. Let's start with the nodes. Def add node self node if node not an self graph self graph with key node equals an empty list. So if we try to add a node that already exists in the graph, nothing will happen. If the node doesn't exist, it will be created as an isolated node. And now the edges. Def add edge self node 1 node 2. We assume that by calling this method, two edges are created, one from node 1 to node 2 and one from node 2 to node 1. There are four possible scenarios here. 1. The two nodes may both exist in the graph. Or 2. Node 1 exists in the graph, but node 2 doesn't. Or 3. Node 2 exists in the graph, but node 1 doesn't. Or 4. Neither node 1 nor node 2 exists in the graph. The method has to take care of each of these cases. To make it easier, let's first check if the two nodes exist in the graph, and if they don't, let's add them. So here's the code. If node 1 doesn't exist in the graph, let's add it. If node 2 doesn't exist in the graph, let's add it. Here we're using the addNode method defined over here. Now we know for sure that the two nodes exist in the graph. Let's add the edges between them. So this creates the edge between node 1 and node 2, and this creates the edge between node 2 and node 1. With the class in place, let's test it. We'll be making use of the graph defined before. First, let's create a graph object and initialize it with our graph dictionary. So G equals graph, and here's our graph dictionary. Fine. Now let's print out all the nodes, all the isolated nodes, and all the edges. Here's the code which does just that. Print the nodes, print the isolated nodes, print the edges. We're making use of the methods nodes, isolated nodes, and edges defined in the class. Now let's run this code. So the nodes B, C, D, and K, W, the isolated nodes, K, just this one, and the edges. There's an edge between B and D, between B and N, and so on. Fine. Now let me comment out this part of the code because we want this not to obfuscate the output later on. And now the transportation company is doing better. You can now travel to Miami. Let's create a new node, M. G, add node, M. Now M is an isolated node. Let's print out all the nodes and all the isolated nodes again. Here's the code for that. Print the nodes after adding M. Print the isolated nodes after adding M. Let's run this program now. So the nodes after adding M, B, C, D, and K, W, and M. The isolated nodes after adding M, K, and M. So it works fine. And now let me comment this out too. And let's go on. We can go from Kansas City and from Washington to Miami. So we'll need two connections or edges. G, add edge from Kansas City to Miami, and G, add edge from Washington to Miami. Fine. Now, two things have changed. First, we should be able to see the new edges. Second, K and M are no longer isolated nodes because they are connected, so there should be no isolated nodes at all. Let's check it out. Here's the code. Print the edges after connecting K with M and W with M. Print the isolated nodes after connecting K with M and W with M. And if there are no isolated nodes, which is the case here, we should get the following message. There are no isolated nodes. Otherwise, all the isolated nodes should be printed out. So let's run it now. The edges after connecting K with M and W with M, B to D, B to N, and so on. And here we have K to M, Kansas City to Miami. Here we have W to M, Washington to Miami. The isolated nodes after connecting K with M and W with M, there are no isolated nodes. So it works perfectly fine. Good. Now let me comment this part out too. Okay. Finally, let's add a totally new edge between two totally new nodes. Let's say there's a second line open between Sacramento and Vegas. So G, add edge, S for Sacramento, and V for Vegas. Okay, let's see if the new edge was successfully created. Let's print out all the nodes and edges one more time. So, the nodes after adding an edge between S and V, and the edges after adding an edge between S and V. Let's run it now. So, the nodes after adding an edge between Sacramento and Vegas, B, C, D, and K, W, and here we have S and V, the two new nodes. And here are the edges after adding an edge between S and V, B to D, B to N, and so on. And here we have S to V and V to S. Fine. Let me comment it out now. And now let's create an empty graph, add a couple of nodes and edges to it, and see what we get. G equals graph. So this creates an empty graph. Now let's print all the nodes, all the isolated nodes, and all the edges. There should be nothing, because this is an empty graph. Print the nodes, the isolated nodes, and the edges. And here is the output. The nodes, nothing. The isolated nodes, nothing. The edges, nothing. So this is what was expected. Let's add a node. This time our nodes will be numbers. So G, add node, and let's add the number 1. Fine. Let me now comment this out. Now 1 is an isolated node. Let's print all the nodes and all the isolated nodes again. So the nodes after adding 1 and the isolated nodes after adding 1. The nodes after adding 1, 1. The isolated nodes after adding 1, 1. This is an isolated node. Okay, let me comment this out now. And now let's add some edges. So, an edge between 1 and 3, 1 already exists, 3 will be created. An edge between 2 and 3, and an edge between 4 and 5. And now let's print all the nodes and edges. The nodes after adding some edges, and the edges after adding some edges. And here's the output. The nodes after adding some edges. 1, 3, 2, 4, and 5. And here are the edges. 1 to 3, it's here. 3 to 1, it's in the opposite direction. 3 to 2, 2 to 3, 4 to 5, and 5 to 4. Okay, that's it for this video. If you like it, a thumbs up would be great. Also, make sure to subscribe for future videos. If you want to leave a comment or ask a question, you're welcome to do so. Thanks for watching.